Welcome. In this video, I'm going to talk a little bit about measures of effect size for two binary variables, so a binary and binary association. There are quite a lot of these, so this video will be a little bit longer than usual, but hopefully it will be worthwhile. I tried to group them a little bit together. The first group are those that will actually be making use of the chi-square test statistic. So usually you do an effect size measure after you've done a statistical test, in this case a chi-square test of goodness of fit. So measures that actually use this are Yule Phi, or the Phi coefficient, the contingency coefficient, and Col C5. Then there are quite a lot that are based on the so-called odds ratio. I have a separate video on the odds ratio itself, so this will be more focused on those that actually make use of that. Yule Q and Yule Y actually use that, and for Yule Y I'll also make a separate video to go a little bit more into details on that one. Edwards Q and Digby H are another two that actually use the odds ratio. Then there are a few others I couldn't really place. There's Forbes Coefficient, Col C1, McEwen and Michael's, which is the same as Col C3, and Col C7. A whole other category are so-called tetrachoric correlations, which includes Yule R, Pearson Q4, Pearson Q5, something from Becker and Clark, Bonnet and Price, and there are also some software algorithms from Camp, Brown, Kirk, and Digby. I won't go into the details of all of these. I'll just try to show you how they somewhat link to each other. So the first one I want to talk about is the Phi coefficient. So if I have a table like this, a cross table with two categories for both variables, I could actually have a look at the original data and have coded it with zeros and ones. So these three people, they each get, let's say female is 0, so then they get a 0, and other is also 0, so those are those three. Then the next one will be a female with the Netherlands, so 0 and 1, and that goes all the way down to person 42, who has then 1, 1 as the scores. If you would then see these as real numbers and simply calculate the traditional Pearson product moment correlation coefficient, so in general you have these values, then this is the formula for that, and that will actually be then the same as the chi-square test result divided over n, and then the square root out of that. We could also write that down in one go, and this is the Phi coefficient. It's also known as Yule's Phi. It's known as Pearson's Phi. Cole dubs this C2, and it's also referred to as the mean square contingency coefficient. So the Phi coefficient is the regular correlation if you would just simply assume that the values would be 0 and 1. Now it was dubbed the mean square contingency coefficient because there's also a contingency coefficient. The contingency coefficient is the chi-square result again over n plus the chi-square result, and then the square root. I have a whole separate video on calculating that chi-square value. That's not the point for this one. So Cole actually noticed that if you use this coefficient, the maximum value will, for a 2 by 2 table, actually only be the square root of a half. So he basically proposed to divide this all by the square root of a half, which you could write out as shown here. So that's actually called C5 and is an adaptation of the contingency coefficient. So the previous measurements, they all used somehow or indirectly the chi-square test result. Another group are the ones that are based on the odds ratio. And I think it was Edwards in 1957 or 64 who actually said that any measure for a 2 by 2 table should be based on the odds ratio. Now, we can generalize the formulas that actually make use of this, and I think it was Digby who also showed this, by saying it's the odds ratio to a certain power minus 1 divided by that same thing but then plus 1. So it was Yule who actually had a Yule Q and a Yule Y who uses this, and for his if x is 1, so the power is simply 1, then you get Yule's Q, and if you take the square root of the odds ratio, in other words raise it to the power of a half, you get Yule's Y. As mentioned earlier, I do have a separate video, or will actually soon make a separate video on Yule's Y. However, Digby noticed that the Yule Q will usually overestimate and Yule Y often underestimates it. So somewhere between 0.5 and 1 might be a more optimal value for that power. So Digby H is actually, he determined himself or herself 0.75. And Edwards Q is also sometimes referred to, which has a value of pi divided by 4, which, if I'm not mistaken, is 0.79 or something. So those are for other measures that could be used. One measure that's also very often mentioned is the Forbes coefficient, of course created by Mr. Forbes, and it's written out like this. It's n times the full sample size times the minimum of the two values in the diagonal, divided over the sum of column 1 times the sum of row 1. And actually that's just if it's A, if it's D, it's C2 and R2. Now, this value has a value of 1 if there's no association, 0, and 2 for a perfect one, depending on if it's a positive or negative one. So Cole therefore adjusts this simply by subtracting 1, and then it can actually be rewritten in the format you see over here, like this. So that's Cole's C1. There's an interesting problem though with many of these coefficients or measures. If you have a table, for example, like this, or even worse, if any of these values would be 0. So here you could argue and think about this for yourself. Is there a strong correlation or not? Because almost all values are here, and the problem is that we have so few in the other categories. So if you would actually calculate this, Yule's Q and the other measures based on the odds ratio will all actually be very close to 1, 0.9 something. Col C will even be 200, C1 will even be 249, so off the charts. And the question a little bit is if that's fair. So Michael, in his article, he came up with a McEwen and Michael coefficient. So he gave credit to one of his colleagues, I think it was, and came up with this formula. So this tries to prevent this and see this as a very weak correlation or a very weak association. So that's what Michael and McEwen's coefficient actually does. Cole actually disagreed a little bit on this and came up with his coefficient of interspecific association. It's based on the premise that you realize that if there is no association, all values should be the same. So all values are also identical to their expected counts. And the expected count can be done by simply taking the row total, multiply it by the column total, and divide it by the grand total. So if this value matches the expected count, then there is no association in the 2 by 2 table. So if we want to see how far off we are from no association, we can simply take that A value and subtract it from its expected value. Cole then determined that how many possible tables with the same margins can you actually make that will have a positive association. And that can be done according to Cole using this formula. So to see this is just an absolute value, divide that over how many there are with a positive one, and you get yourself a new coefficient, which in this case boils down to this one. So this is simply taking the difference and divide it over this one, And if you do some extra work, you can actually manipulate it to be the same as this. He actually gives a few additions if this is not true. So if A times D would be less than B times C. If you're interested, on my website I have the full formulas for that as well. The last group are so-called tetrachorical correlations. Now, this can be defined as an estimate of correlation between two random variables having a bivariate normal distribution obtained from the information from a double dichotomy of their bivariate distributions. So these actually assume that the values in here are actually this one, this variable, and this variable, we're actually having an underlying normal distribution, so that they would have something like that. Then they come, this is hard to draw, like that. And then you can combine this into a bivariate normal distribution, which is different than the standard normal distribution, which has a specific correlation coefficient. Depending on how that looks like, you might get something with high values around here at a specific correlation. And that's what these tetrachorical correlations actually try to figure out. Now I have a lot more on the bivariate normal distribution if you're interested, but the correlation is in essence trying to do the opposite, tries to find what the correlation would be in order to have this specific value there. Since this is quite tricky to actually do, there have been some formulas that try to approximate what then the tetrachorical correlation should be. So Yule was one of the first who actually came up with one of these. This is his formula. Pearson had a similar one, and also Cole had his C6. All these three are exactly the same. So the Yule's correlation, the Pearson's Q3 and Cole's C6 will give you the exact same result. So these were just approximations for the tetrachorical correlation. Those are not the only ones. Pearson's, besides his Q3, he also has a Q4 and a Q5, which are slightly different ways to get to that tetrachorical correlation. And there are, for example, Becker and Clock, and also Bonnet and Price, who also came up with some kind of equations that are a little bit longer and more complex than the other ones. So I'm not showing them here. If you're interested, I do show them on my website. Besides formula approximations, there are also some computer algorithms or algorithms in general that some people made. I found one by Kemp, for example, in 1934. There's one by Brown that's quite often used. There is Kirk and there is Digby, who all came up with algorithms or sometimes some Fortran code to actually calculate these, the tetrachorical correlation. I've made for some software packages, I try to actually incorporate these, so if you're interested in that, they're available on the website. That goes for all the measures. On the website I have an Excel file, a Python script, an R script, and Flogorithm charts that show for all the measures how they can actually be obtained with some examples. So including the algorithms and all the ones that you've seen in this video. So if you're interested on how to actually calculate those, have a look at those files depending on which software you're using. Right, and that was a quick, brief overview of various measures of association. I'm bound to have missed a few. If you do have another one that's not too complicated, let me know. I'm always interested in seeing other ones. I hope this made a little bit of sense, and thank you for watching.